All right, well, we've discussed Quicksort implementation details, and we've proved that it's correct. Let's wrap up our Quicksort discussion by talking about the running time. So that's what the focus of this set of slides will be on, is just purely looking at the running time. Well, what is the running time of Quicksort? And it's a recursive style algorithm, a divide and conquer algorithm, so can we use the master theorem? And the answer to that is, again, no, because our recurrence equation for Quicksort has a flaw to it, in that it doesn't split things up into even calls. There's no way to, this equation here doesn't follow the master method sort of template for solving recurrences. Remember, the master method looks something like this. It only solved when we had a times t of n over b plus big O of n to the d. That's not what we have here. We have two separate calls, each with a different amount of data. So we can't use the master method. And what is Quicksort's running time? It depends heavily on the element selected as the pivot. And in our exercise here, you'll see why it depends so heavily on the element that's selected as pivot. So what's the worst case running time for Quicksort? And what's its running time? And then, sorry, I thought the next one would come up first, but so what's the worst case running time for Quicksort for selecting pivots? What's the worst possible pivot you could select, and what running time does that lead to? I'll pause the video here and let you answer that question. All right, well, what's the worst possible pivot we could choose? It would be when we don't have a balance between the left and right recursive calls. So what gives us the worst balance between the left and right recursive calls? It's if we pick something that's a maximum or a minimum element. So if we always select the smallest value as the pivot or the largest value, we're actually going to end up with a big O of n squared running time. And I'll show you that on the next slide, actually. You can think of this as a one-sided recursion tree, which I'll draw on the next slide. What's the best case for Quicksort? Well, the best case for Quicksort is we always select the median element, and that leads to a running time of big O of n log n. Think about it this way. If you select the median element, we can actually use the master method. If I told you I guarantee you that we'll select the median element every time, that means we have two recursive calls, each with half the data, which would give us the same recurrence equation as merge sort and closest pair and a few other algorithms, which is going to give us big O of n log n. So best case is big O of n log n because we are evenly dividing amongst the two recursive calls. So let's look at some recursion trees when we have the worst and best cases. So let's say we have n elements, and let's say we take the worst possible pivot of the minimum value. That means there's nothing over here, there's nothing to the left of the pivot, and n minus 1 elements to the right of the pivot. Let's say we get unlucky again and we pick the minimum now, so the second overall smallest. There's nothing this way, and n minus 2 elements this way. And let's say the next time we get unlucky by taking the maximum element. So there's nothing to the right of the maximum element, and n minus 3 elements here. And if you were to keep doing that all the way down to where you get 1 element, you're going to end up with a tree height of what? Well, the height of this tree would be n. And at each node, we're calling partition, which is big O of n work. So we'll end up with a running time here of big O of n times, which is n squared. So worst case is an n squared running time of Quicksort. What does it look like in the best case? Well, in the best case, we're always going to pick the median element. So maybe we have n over 2 elements this way, and n over 2 elements this way, minus 1 because we removed the pivot from it. And then same thing here, n over 4 elements, n over 4 elements, and I'm not going to worry about the minus 1s here just so I don't have to carry them through everywhere. N over 4, n over 4, all the way down to where we get 1 element everywhere in the leaves of the tree. So what's the running time, or sorry, what's the height of the tree under this scenario? Well, the height of this tree is going to be roughly logarithmic. It's a little different because of these minus ones here, but it's going to be big O of log n. It's going to be in that range. And at each level, we're going to call partition at all these nodes. But if you look across the entire level, we still have just n elements. So we're calling partition on effectively all n elements. So we're going to do big O of n work times the height of the tree, and that's where we get n log n total work for the best case of quicksort. If you want some concrete numbers on this, let's assume that the partition cost is 5m, and let's say that we have 8 elements. Well, that would mean if we have 8 elements and we're calling partition on it, we're doing 40 computations. And in our worst case tree over here on the left, we now have n-1 elements, so we're going to call partition, which is 5m, where m is n-1 here, 35 units of work. And it's the same on the right-hand side. So if you notice, we do 40 here, 35 here, 35 here, because we still have the same number of elements. So where do we get the benefits of having a divide and conquer algorithm? It's in the height of the tree. So you'll notice that these elements are pretty close to what we have here on the left-hand side, but this left-hand tree keeps going down, and it requires us to call partition a greater number of times. So the total cost over here, in sort of absolute terms, if we're assuming 5m is the total cost of partition, is 180, and over here it's 105. So quite a bit better on just a size of n equals 8. Alright, so how would you select the pivot? If the pivot selection is so important, shouldn't we spend a great deal of time selecting the pivot? Well, it turns out that you can get away with selecting the pivot uniformly at random, and we're going to prove that that's a good idea. And the reason this works is because it's easy, it's fast, and it gets good pivots decent fairly often. So it's good enough, often enough, for us to get a good average running time. Alright, so the rest of this set of slides will sort of dig deeper into this idea of using a random pivot selection.